Okay, first of all, welcome back from the tea break. I hope you're now fully awake after the tea break. I know that some of you had a late night last night, and this morning was a bit groggy, no breakfast, and then somehow, So now after the coffee, I hope you'll be much better. Now, we have just covered the modified chem clay this morning, and I want to say something about limitations of chem clay in modeling real soil behavior. Now, as I mentioned to you, there's no such thing as a model that will 100% model real soil behavior. 100%, no. Even something as simple as Singapore marine clay, the marine clay we have in Singapore, actually the behavior is actually quite complicated. And I'm going to show you some test results and what are the problems of modeling that behavior. Okay, some of the limitations. This is not an exhaustive list, but I think it's basically show you some of the main problems. Firstly, it cannot model the loss of structure in many natural soils. Okay, usually refer to cementation. Now, the chem clay class of model, and in fact, that I think also includes the Plexis hardening model and the Plexis soft soil model. Is not meant for cemented soil or structured soil. They are meant for, in a sense, remolded soil. In fact, the early chem clay models were all done for remolded soil because you keep kaolin powder come in and they mix it up in big pots of water and things. And so it's all remolded. There's no such thing as natural structure. So as a result, it is really not applicable to soil. Well, it is applicable, but you need to be careful. There's some error involved in modeling natural soil behavior. One of the things about natural soil is that quite often there is a certain amount of structure. Okay, and when I talk about structure, I'm talking about something that is cementation is one kind of structure. Fabric is another kind of structure. Particle alignment, orientation, all these are structures. So basically, one of the common thing that we found out, about Singapore marine clay, and that to me highlights a very important aspect, and that is that something as soft as marine clay, 20 kilopascal, when you really test that guy in an undisturbed condition, you find that it's actually moderately cemented. Okay, moderately cemented. There's a small amount of cementation, and it makes a lot of difference to the behavior of the soil. So this is one of the things that you need to watch out for natural soil. And the second thing is that the elastic behavior of soil is not modeled by chem clay. The reason is because when the guy first started chem clay, they were all looking at the wet side of critical. And so on the wet side of critical, the soil is lightly over consolidated, it's normally consolidated. The moment it yields, the plastic strain will overpower the elastic strain. It's much larger than the elastic strain. So whether you model the elastic strain properly or you don't model it properly, you get a reasonably good prediction. Okay, and as a result, nobody who developed the chem clay model, it was not the elastic portion was not developed. It was just assumed. And different people assume slightly different thing. Okay, and this, but in particular, is not modeled by chem clay, not modeled well by chem clay. This is particularly important in heavily over-consolidated soil. So I will continue on forward. I will say something more about this, but these are some. And the K0 value is not exactly the same as that predicted by J-Key's relationship. I have already mentioned that, but I'm not sure if that is really a limitation, because although a lot of us believe that J-Key's is the reference, but there's nothing to say that J-Key's is the correct value. Okay, so we also need to be careful about that. Okay, now, just to recap, what is the contribution of the chem clay models? And since chem clay, I can tell you that in terms of models alone, based on chem clay, maybe a few hundred to a few thousand already. Critical state model, a few hundred to a few thousand has been proposed. A few hundred. In fact, David Wood, in one of the international conferences I attended, he traced the, family tree of the chem clay class of models, starting with the original chem clay, the modified chem clay, and then all the subsequent modification. It went into there are quite a lot of models based on chem clay. So there's no shortage of models, and they all do slightly different things. Okay, basically the two major contributions, as I see it, of the chem clay class of model, whether it's original chem clay or modified chem clay, is this. The first is the 3D framework. Remember, I asked you to think 3D instead of 2D. And let me just reorientate. And this is one point that, in a sense, I'm glad I come upon this slide because it slipped my mind when I first introduced the 3D framework to you. This is the 3D framework. And this is the Q-axis going up. Agree? Okay? Now, when we learn classical soil mechanics, we are taught two different things. One is consolidation and one is shear strength of soil. Okay? Now, the thing about consolidation and shear strength of soil is this. That when you do 1D consolidation, when you do one-dimensional consolidation, I hope I haven't messed up the board. When you do one-dimensional consolidation, okay, you would plot a log of, this is natural log, a common log of the overburden pressure. We don't call it P, let's just call it sigma V dash. The vertical overburden stress, vertical effective stress, right? Because you are doing one-dimensional consolidation. So you'll be using vertical effective stress. Okay? And down here you have the void ratio. Okay? Now actually this is your compression space. Alright? You would have something that looks like that and then something like that. Is that okay? This really is the compression space. Now, then when you come to shear strength, okay, your professor will tell you, okay, we plot this. And then you got this. Agree? That's a more Coulomb. Now, the thing is that, if I'm not wrong, in fact, I think that probably most, in fact all, 99.9% of the time, these two aspects are considered to be, in a sense, unrelated kind of issue. This is shear strength. This is compression. What critical state soil mechanics and this 3D framework tells us that, in fact, they are related. They are related because this is a measure of the normal, this is a measure of effective stress. This is a measure of effective stress. By right, they should be related. So if you can make this axis in such a way that this axis here is common with this axis, then this becomes the wall of the house. This becomes the floor of the house. So in fact, the 3D framework is a way to combine these two ways of looking at soil into one single framework. You know what I mean? Into one single framework. The idea of the framework is that as you consolidate the soil, your strength should go up. That has to be the case. There's no other way it can go. It has to go up. So basically what they say is this. Instead of plotting this, why don't we plot this? We plot P dash. You can leave this as E or you can put it as specific volume. It's just 1 plus E, no issue. Alright? Then instead of this, you plot P dash. This is a measure of effective stress. That is a measure of effective stress. And I plot Q over here. This is a measure of shear stress. And when you combine the two, you realize that this immediately is the wall of the house over there. That is the floor of the house looking downwards. So basically the 3D framework is really a way of combining the two views of soil behavior, strength and compression. Is that alright? So when you think of it that way, actually the whole thing comes out, it's quite neat because by right, I expect the soil strength to increase as it becomes more consolidated under a heavier effective stress. And in fact, this framework tells me that this should be the case. So this is one nice thing that comes out of the chem clay, of the critical state soil mechanics framework. So basically, it combines the phenomenon of strength and compression into a single framework of behavior, 3D. Okay? The second thing about the chem clay behavior is that chem clay makes a very clear difference between peak strength and ultimate strength. And as far as chem clay is concerned, failure is ultimate strength. Okay? Peak strength is basically associated with yielding, more associated with yielding rather than ultimate failure. Okay? And in chem clay, yielding including virgin compression, that means this virgin compression line, is attributed to the beginning, the initiation of large-scale particle slippage. That means you got particles starting to slide past. Rearrangement, okay, rearrangement. I mean, and in a sense, you can see why it is plastic. Suppose you got a bunch of particles and you press it and the kind of particle rearrange and repack itself. If you let go, if you unload it, if you allow the load to go, will the particle automatically unrearrange itself? It can't. Particles will not unrearrange. They will just stay in a new arrangement. And that is essence. And in essence, you can describe it using plasticity. Is that all right? So that is the thing. So basically, elasticity in soil, we usually think about it, the way we usually, this is our mind, the way we think about it is a mind mapping kind of thing. You know, when we think about elasticity, it is, particles are not slipping, they are just sort of compressing, moving, but the contact points are maintained between particles. All right? There's some compression. Okay, slipping, when you go into plastic state, whether it's shearing or whether it's compression, the particles are all rearranging and repacking itself. So once it is repacked already into a denser formation or looser formation, you cannot unpack it. You cannot unrepack it. You know what I mean? You cannot unpack it again. You cannot come back to the old configuration. So this is what is happening. So the yielding is always associated in soil with particle sliding and slippage. Okay? In cemented soil, it is usually associated with particle rearrangement, but particle rearrangement requires the bond to break. If the bond don't break, the particle cannot rearrange. Right? So therefore, as a result, basically it is also associated with the breakage of the initiation of the breakage of the bonds. The breakage of the bonds. Okay, so this is basically what happens. So basically, it clarifies the difference between yielding and ultimate failure. Now, it turns out that the critical state concept has been used in certain code of practice, and I want to mention PS 8002 just in case you come across British Standard 8002 for retaining structure, and they actually use a lot of critical state. There is a mistake in the notes. Please write it down. It says, the note says that it should be factored down. But I missed out the word, very, very important. It should not be factored down. Can you please put that in? It should not be factored down. This one. Okay? It should not be factored down. Now, the BS 8002 basically says that there are two things here. How many of you are familiar with limit state design concept? Limit state design concept. Have you all done limit state? Basically, they always classify limit state into the ultimate limit state, and a serviceability limit state, right? The ultimate limit state is the ultimate failure, and usually the PS says that at ultimate failure, you're talking about stability. Really stability. The thing is collapsed. Okay? So when you're dealing with stability, the BS says that the thing that is applicable is the critical state, and it should not be factored down. You should use the full critical state strength. And this is in recognition for the fact that, in fact, the implied factor of safety, the implied factor of safety based on the limit state approach is sufficiently low that certain parts of the soil must have gone past the peak strength. So they said, actually the soil has gone past the peak strength, so you cannot use the peak strength, you should use the ultimate. This basically come back to the Mike Duncan's thing about some people using 1/4 peak plus 3/4 ultimate, half peak, half ultimate, 3/4 peak, 1/4 ultimate, that kind of thing. But so the BS 8002, the stand is very clear. For stability, you use the critical state. Okay? So basically, but you don't factor it down because they said the critical state is already very low. It's already very low. Okay? So this is the first requirement. The second requirement is deformation limitation. Not deformation assessment. Actually, it's the wrong word. Actually, limitation to restrain deformation. That really is a serviceability limit state. Okay, to make sure that the deformation, the ground movement, is not so large as to cause damage to the neighboring structure, the retaining wall, or what have you. Okay, basically, what they say is this: you should not allow your soil to be stressed past a certain percentage of the peak strength. a certain percentage of the peak strength. Maybe typically about 80%, 70% of the peak strength. That is the kind of thing that there is a factor that's given. They call it the strength mobilization factor. The strength mobilization factor. So basically, if you look at this stress strain curve, British standards actually says that if you are looking at stability, you would use this point, which is the ultimate state. This is the ultimate limit state. If you are dealing with serviceably limit state, you will take this but factor down to a certain level, maybe down here. So you will use this. Alright? And the way they work is this. You don't have to do two designs. You just do one design. You use the lower of this or this in your design. Is that alright? You either use the lower of the peak divided by the mobilization factor or the critical state. This is the way the BS 8000, and I was quite familiar with it because we were using it quite a lot. In fact, the factors used in the BS 8002 are actually adopted by the EC7. Okay. Now I know someone, one of my colleagues, KK Poon, who's a big name in risk analysis in geotechnical engineering, reliability analysis, geotechnical variability. He's big name in that, KK Poon. You know him, right? He's very, very, very famous for that. One of his papers, I think, has been cited 500 times or something like that. His PhD work, geotechnical variability of soils, very, very famous. Now he was very close to people like Brian Simpson and the people who are. Brian Simpson was the chairman of the committee that wrote the BS 8002. And he was also responsible for, in a sense, bringing together the BS 8002 and the Eurocode. You see, there are different things, different group of people believing different things. The Europeans believe in partial factors, where they say, okay, I'm going to partially factor the uncertainty of the soil, the workmanship, the blah, 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 the uncertainty in the load, etc. So this is the European approach, which was actually what they call the Eurocode. Okay? And then the British have their own approach, all right, which is also another way to look at limit state approach. That was the politics of it. And then the Americans and the Japanese are not on board. Okay? The Americans still love the factor of safety. They are still very happy with the factor of safety. There's no need to change factor of safety. The Japanese, no need to change. The Japanese also love factor of safety. There's no need to change factor of safety. So basically, the Eurocode people have a lot of problem pushing their Eurocode to become an international standard. You know what I mean? To become an international. They are always trying to do that. They are still trying to do that. But I think with the American against it, very difficult. The American is a huge block of things there. The Americans just don't give a damn to the International Society of Soil Mechanics and Geotechnical Engineering, which is dominated by the Europeans. Continental European, not the British. The British are very suspicious of the continental European. This is two European people divided by a common channel. The British, what British channel? They call it the British channel. I don't know whether Neil Taylor told you the story of why he became Secretary General. He was the Secretary General when you were there. Yeah, he's been there. He's asked to be there forever. He's not there forever. He's asked to be there forever. I believe the story was that Berlin said, you better become the Secretary General because the blooming Europeans are going to dominate the whole thing. Because the Europeans got Pinto, they got Van Impe, they got all kind of people coming in. There's a whole string of presidents of international society coming in. And the Europeans intended to dominate the whole thing. The Americans don't give a they don't give a damn, You can do anything you want to. I believe I got my what they call it, Geo Institute. The Geo Institute to me is the ultimate, I can play along with you on some international conference, but you ask me to do your thing, forget it. I'm not going to dance with you. And the Americans are big enough to tell them to go jump into a lake or something like that. So basically, the Americans don't care, and the Japanese also don't care. The Japanese are very insular. I mean, I got all my code of practice. Why I want to listen to you, So I don't know India. What do you all do? Whether you listen to them or you don't listen to them. Do you use the Eurocode? You use the Indian code, right? Yeah. Right. But do you use the EC7? So basically, you're following the American and the Japanese. So you can see the Eurocode is not getting audience. And in fact, in the early days, the Eurocode couldn't even capture Britain. Because Britain has got PS 8002. So the Eurocode now, the way they water the Eurocode now, I tell you it's a joke. They give you 3 options. You take the first option, that is a standard Eurocode option. With a lot of partial factor, factoring the load, this kind of thing. The second option actually reduces to PS 8002. It's nothing. It's nothing but PS 8002. All the factors are PS 8002. The third option is your classical factor of safety. So now the European position is essentially in the Eurocode. If you read it in concept, like you examine it in concept, it's a statement of saying you can use anything you want. I cover everything. You know what I mean? It's not saying anything, but I mean, you must be thinking, if I use anything I want, why don't I just use my own code rather than your code? Of course, yeah. But the Europeans just want you to say you are using Eurocode. Okay? In actual fact, you are using factor of safety, your own factor of safety. It doesn't matter. I can show you the Eurocode, what the Eurocode says afterwards. But the PS 8002 is essentially, there is a critical state concept built in. So when you read the PS 8002, be very, very clear. Because the PS 8002, in the beginning, they talk about critical state. They talk about the angle of the failure envelope and how the failure envelope changed with the thing. And you can see that for over-consolidated soil, the failure envelope given to you is actually a curved failure envelope because it's associated with the U locus for the peak strength. Okay? So this is how the PS 8000 looks like. Now, how many of you are interested? I have actually got a copy of PS 8000. I can flip through it very quickly for you if you want to, but only if you want to. How many of you are interested in just saw? You are interested? Okay. Because I thought that if you're not interested, we'll just move on and, But if you're interested, no problem. Because I got all my stuff here, so we can just... And this is not a pirated copy, so I dare to show you. It's actually, we actually have a university license for this. So we are quite okay. They actually tell me that. Okay, so if you PS 8002, just running you through very quickly. The nice thing about the PS 8002, I also like this. I'll just quickly run through it. These are the people involved, Brian Simpson. Brian Simpson, if you want something about the background, PS 8002, go and read up Brian Simpson, Dr. Brian Simpson, Brian Simpson here. His ranking lecture, 1992, I think. Is completely on the background of PS 8002. How they come up to all these factors and all these strength mobilization factors and all the rest of it. So this is all there. Okay? So the first part is nothing but just some definition. Then after that, let me just quickly run you through. Okay, there's talking about general site investigation. What you need to do is, a lot of it is, you can think of it as motherhood statement, okay? But these are some indicative soil parameters. And this is something useful to me because they are giving you, let me just shrink it down a little bit so that it's back to something you can see a bit more. Okay, can you still see the words on the screen? Yeah? So basically, these are some indicative values. Now, usually the way the PS 8002 works is this. They will give you the the more conservative value. Alright? So basically, like friction angle, when they specify a friction angle for you, usually it is likely to be on the conservative side. So if you don't have any other value to use, this is one source of information you can look up. One source of information. Okay? So you can see things like, first they start off with the unit weight. So they give you the unit weight. After that, they went through, they will go through things like clay soil. And then they talk about plasticity index and the critical state angle of friction for various soil with various plasticity index. Okay? Now, I actually checked this out for Singapore marine clay. The thing that come out was about 2 degrees lower than our measured angle of friction. So it is on the conservative side, no doubt. Okay? So these are some of the angle of friction that they can give you. But on top of that, there are other things. Now, this is where the critical state soil mechanics concept come in. They actually explain to you, you see the peak, what they say is that if you have a soil consolidated in this particular range over here, in that particular range over here, Failure envelope is curved because they said you are taking the peak strength. And the peak strength is associated with the U locus. Remember what we said just now? It's associated with it. But if the soil is not normally consolidated, you won't see a peak, not heavily over-consolidated. If the soil is slightly over-consolidated or normally consolidated, you will not see a peak. You will just go all the way up and it hit critical state. And if you do that, if you plot it out, you will see a straight line. That is the critical state, projection of the critical state line. You understand what I mean? So basically, there is a lot of, you see the critical state, this is the critical state, this is a peak state. They actually draw the difference between the two. So basically, there's a lot of critical state concept being utilized over there. Okay? And then they will tell you how they actually factor down. And then the residual strength is different. You can see the residual strength, the residual state here is much, much lower than the critical state line. This is the straight line starting from here is a critical state line. The lower line is actually the residual state. Okay? So basically, this is the situation. And then, to me, this part is very useful for these people who are looking at cohesionless soil design. They actually have a way for you to pick, to calculate or infer the angle of friction, the peak angle of friction of the cohesionless soil, starting with the minimum lower bound, sand for sandy soil, cohesionless soil, sandy soil, based on 30 degree as the lower bound. So what you do is, you see, 30 degree plus A plus B plus C. Okay? Now, A is a certain parameter you can add in based on the angularity of the particle. B is another parameter, a few more degree you can add in based on the grading of the particle. And C is the result of standard penetration test. And then they give you, for example, this is A, B, and C. So these are, for example, angularity for rounded, subangular, and then angular. So if the soil is very angular, you can add 4 more degree to your critical state. And if the soil is very well graded, you add another 4 more degree to your critical state. But that is still critical state. Then you say, okay, what about the peak angle of friction? The peak angle of friction depends on your SPT. So depending on your SPT blow count, okay, if your SPT blow count is very low, your sand is very loose, you don't add anything. If it is high, you add additional thing. So this is actually quite useful for design processes. And what they say is that if you're at a loss, well, you can do that. And then for different mineralogy, different minerals, you can also use this. So for those of you who are doing design or even research, this is actually quite a good authority. After all, it's a British code of practice. You know, nobody is going to say, hey, is this real or not real? You know what I mean? So basically, it's a good information, source of information. Now, I just want to go jump over to the part where they talk about strength selection. Okay, this is one. Okay, so this is where we talk about the strength mobilization factor. And they said the design angle of friction is calculated based on the representative angle of friction, representative tangent of the angle of friction, divided by a strength mobilization factor. This is to take care of this part, the first part over here, is to take care of the serviceability limit state. Alright, you see this is part A. Part B is the representative critical state of the soil. This is to take care of the stability, the ultimate limit state requirement. So they are considering 2 limit states here. One is serviceability, one is ultimate. Okay, so this is exactly how you do it. So the M value that you use typically is about 1.2. That gives you about 80% of the value. If you are using effective stress, and if you are using total stress, I think it's a bit higher. The mobilization factor is like 1.4. So you actually have to factor it down a bit more if you are using CU alone. So this is how the British code is done. So that is exactly how it's done. So this is just a quick view of the BS 8002. Of course, there are a lot of other things. And they have very nice design charts on earth pressures and things like that, which they collected together, which I thought is actually very useful and general formulas. You know? So it's actually very useful even as a design manual of some sort. So yeah, you can take a look at it if you have access. Do you have access to IIT? You all have access to this. Should have, right? Do they have access? Yeah, all available. So I think you can actually tap tap on all this. So, okay, now let me see whether I can, I have a set of thing on the EC, what do you call it, the EC7, the Eurocode. How many of you are familiar with the Eurocode? You are familiar with the Eurocode, right? Okay, the Eurocode actually has three things. I think you are familiar with the three option. Let me just. I see whether I have the Eurocode here. Okay, so the Eurocode. I only want to show you one table. And that's a table that basically shows everything. Okay, basically you can see these are the combination of, it's actually, it looks very confusing. It looks very confusing. If you look at this set of factor, this is really the BS 8000 factor. This is the BS 8000 factor. Alright? Okay, this is the BS 8000 factor. So basically you can use the M2 factor. You see the combination they allow you to use is, you can use design approach 1, which is the A1 plus M1 plus R1, or the design approach 2, which is the A2 plus M2 plus R2, which is actually the BS 8002 approach. The A1, M1, R1 is actually your factor of safety approach. So if you look at the A1, M1, the design approach 2 and 3 is their own Eurocode thing. So most people, they won't bother with the Eurocode thing. I mean, I will just, for example, if you look at A1, M1, R1, A1, they look at the loading factor. If you look at the loading factor, you got variable action and accidental action and all that sort of thing. But you look at, most of the numbers are 1. You see that? Except for dead load and live load. That's all. Okay? So this is your factor of safety, dead load, live load. And you look at the material. How do they factor the material? A1 plus M1. M1, everything is 1. There's no factoring. There's no factoring at all. So if you use A1 plus M1 plus R1, everything is also 1. You know, in R1, everything is also 1. So basically, the only thing you factor is the dead load and the live load, which is your factor of safety. You see? So basically, this is the way the game is being played by the European, whereby they say, okay, since people don't agree with me, I accommodate them. As long as they tell people that they are using Eurocode, that's fine. You know, which is of course a real cop-out, you know. But never mind. So you can use their code or you can don't use their code. You can say use the code and say I use design approach 1, A1, M1, R1, or you can say I don't care, to the hell with them. The American does that, they don't care about them. So they will just carry on their own thing, you know. So anyway, that is BS 8002, how the critical state concept come into the picture. Okay? Okay, I want to say a little bit about heavily over-consolidated soil. And this is to me, this is a trick. Some of you asked me about what happened if I got a shear bend happening. Now, this has been something that has been studied since the 1970s. And in fact, in the 1950s, Roscoe, Schofield, and Roth wrote a paper which is somehow by now not very well known, talking about quality of triaxial test data. Quality of triaxial test data. It was written in Geotechnical Special Publication, GSP, or is it Geotechnical Testing? No, Geotechnical Special Publication. One of the ASCE conference anyway. So it was written up and it was talking about this. And basically what they say is that if you have a soil that has a slight tendency to even drop like that, then you have a problem, because what happens is this. Supposing you have a soil that has a tendency in the drain situation to go like this, to come up and then you go like that. Then you have a problem because it is very hard for your sample to maintain uniformity. And this is something for those of you who are doing triaxial tests, you need to watch out. Okay? So don't believe your test result all the time. Think about it. Okay, I always like to take an analogy of this analogies. Supposing you take a chain, you know, a dog chain or bicycle chain, some kind of chain link, and then you take a series of chain, and then you start pulling it. I tell you that all these links are made of the same material. They are made by a mass-produced process. So by right, they should have all be uniform, right? The property should be uniform. So you start pulling it like this. Okay, you keep increasing until the chain breaks. Will all the links shatter at one time? One will go, right? One link will go. Why? That happens to be the weaker one. Because the stress strain curve of the link is like that. Just go up and then come down. The extension curve is like that. So what happens is that supposing you got one link that has a slightly lower peak force, something like that, that guy will be the first one to go, right? So that guy will then immediately drop here because it fractured. What about the rest of the link? They will immediately unload back. They go elastic unloading. Okay? So basically, supposing this is the weak link, it will go, and then the rest will just unload. Because they can't transmit the stress across, the rest will just unload. So basically, this is an event that in soil mechanics, we call it a bifurcation event. A bifurcation event is where part of the soil goes this way, the rest goes this way. You get what I mean? You got two eventualities, two ultimate situations. And the part that goes this way, the part that goes down the A path is actually the shear band. The shear band will continue to shear at increasing the strain. But the rest of the soil over here will actually come down this way. Okay? Now, the difficult thing with this, with controlling this is what, because your shear band is very thin, relatively thin. So your shear band actually is very hard to keep your shear band undrained because your shear band can easily suck in water from the surrounding region. So you can turn off all the valves to the sample if you like, but you cannot prevent water from flowing into the shear band. In that sense, the triaxial test is not, there's no such thing as a true undrained triaxial test. In the early days, they call it a constant volume test. Because all you do is to maintain the volume there constant. But the shear band can still take in water if it wants to take in water. Is that alright? So as a result, it's very hard to preserve. That's why a lot of people say, can you truly preserve an undrained triaxial test? The answer is not easy. Not easy. We tried it with cement-treated soil, again shear band. The only way you can do it a little bit better is by doing this. You have a sample. You see, one part of the problem with the shear band is that if you observe the shear band properly, very often the shear band will either arise from here or here. This is where the end cap will punch into the sample and cause a stress concentration. So the first thing is to use an enlarged platen. Alright? And then you need to put in frictionless platen. Okay? We use Peter Rowe's kind of method to enforce frictional platen by using two pieces of soft rubber with grease in between. There's hardly any friction there. And he sliced up the soft rubber in a star-shaped fashion so that you allow it to expand and contract very easily. So that is the thing. It's enlarged platen, but we also use short sample. You see, if you look at the inclination of the slip plane, most of our sample is 2:1 aspect ratio. 2:1 aspect ratio. And there is room for the shear band to actually occur. But if you use a short sample, then the shear band, you actually inhibit the formation of the shear band. But when you have a short sample, you have to be very careful because any kind of end friction will actually affect your result. So you must make sure that your friction reduction is very, very effective at the end. And on top of that, you need to have your ends bigger than the sample. Okay, so this requires special attachment. That's why in practice, usually, this is not something that's done often. Is that okay? But if you want to do it for research, you can try doing something like that. We did it, and we got some measure of success. Okay, instead of a big shear band going like that, you get diffuse shearing, and your stress strain curve, instead of having a sharp drop going down like that, in an undrained situation, you get a very gradual drop going down, which I think is more representative of the real situation. Okay? Because once your shear band starts going, then the strain here can build up very rapidly. Externally, you may measure a strain of 20%. Internally, this could be a few 100% inside the shear band. Okay? So this is one of the things that you need to may want to be careful about when you're just doing triaxial testing. Okay, okay. Now, the other thing is from the viewpoint of design, how do you deal with a situation where the sample is obviously doing this kind of thing? Okay, from the viewpoint of design, designers usually don't like to sit on this part of the curve. They don't like this part of the curve. They want to be on this part of the curve. And that is exactly what the serviceability limit state says. You want to be on the pre-peak, don't want to be on the post-peak. In fact, you don't want to reach the peak, you want to be away from the peak by a certain amount. So basically the idea is this, you want to model this part here very accurately. If you have a material like that, then if you have a material that looks like that, then the important thing obviously is to make sure this part is accurate and to make sure your stress don't exceed a certain level of the peak, a certain percentage of the peak. Okay? Now this is where the weakness of the chem clay is. The weakness of the chem clay is that this part is completely lousy. This part is very poorly modeled. And so that's the reason why people say, for over-consolidated soil, don't use chem clay. For over-consolidated soil, there are lots of experimental evidence that in fact, when you shear a soil from very small strain to very large strain, the shear modulus actually drops. Okay? Shear modulus usually drops like this. And this limiting value depends a lot on the soil. The value I cited here is for our marine clay, which is about 20 microstrain, okay, to about 40 millistrain over here. Okay? So basically this is the classical reverse S curve. The classical reverse S curve. Okay? So basically you need to be able to model something like that. And a model like hyperbolic probably give you a better chance of doing that. Alright, in that region. It is elastic, but you are able to model that turnaround. Okay? And this high value here is associated with the fact that right at the beginning, the tangent stiffness here is very, very high. The tangent modulus is very high. And then as you go up, the tangent modulus will drop. Okay? And so the idea is that you need to model this reasonably well. So when I model a soil like that, usually, okay, a lot of people, including people like Richard Jardine in Imperial College, they will just use a more Coulomb and they will just, on the elastic portion, they just fit in a curve that looks like that. Now, this is something that if you are using the hardening soil model, I think there is some facility for you to reproduce this. Alright? But the problem is that the hardening soil model assumes a certain unloading, reloading modulus and assumes some kind of drop for you, which may not work for your soil. This is something that you need to check out. So don't just simply apply assume value from the Plexis manual. Or it's not Plexis, it's just by default, they will just assume for you. Is that okay? Alright. I have nothing against Plexis hardening soil model. It's just that people are using it without sufficient a lot of people are using it without sufficient experimental evidence to show that it is actually that kind of behavior, that the numbers are correct. Okay, so just make sure you got the numbers correct. Okay, and these are some real data from marine clay, and you can see how the shear modulus actually drops. Okay, from the maximum shear modulus to something very low. Okay, so and this drop takes place during over about from 20 microstrain to 5 millistrain. Okay, so these are some of the data that we collected. Now there are different methods used to model this. I'm not sure exactly what method did the Plexis hardening soil model use, but I'm sure it is either a power law or using some kind of generalized hyperbolic. That's the kind of thing that people usually use, okay, to do that. I have a model myself basically on a non-linear chem clay, which does the similar thing, okay? That's the similar. In fact, Ganesh Dasari developed a strain-dependent chem clay model in which he did all this kind of thing. In fact, it was also implemented I think it was implemented on Abacus, but not in a commercial version. It was implemented by himself on Abacus. So these are some of the ways that people can use to do it. Now, anisotropy is another thing you need to watch out for. The only thing is that anisotropy is a very, very wide field of study. You got inherent intrinsic anisotropy, you got stress-induced anisotropy, you got all kind of anisotropy. So it's not a topic you can easily put your finger on and say, maybe I'll give you some guidelines. So for this reason, My only thing to tell you is that if your soil is highly anisotropic, you may find that none of the models you used in Plexis, GeoFEA can deal with this anisotropy. Okay, not easy to deal with. Because the U locus is not, you see the one thing about an isotropic model is that in an isotropic model, your U locus is centered around the horizontal axis. In an anisotropic model, the U locus is centered around perhaps the K0 line. And then that completely, it gives you a completely different picture. You get what I mean? So as a result, you need to be, if the soil is strongly anisotropic, it might be better to just use something like a more Coulomb or something like that to get past it. Okay? Okay? But there are ways you can tune it so that you are conservative. Even in an anisotropic situation, you probably will have to neglect certain aspects of the behavior. So as an engineer, you have to decide what are the behavior I need to neglect to get the thing right. Otherwise, I'll be writing my own model. Okay? So, okay, now I just talked through some of the soil model. The first is the Duncan Chang hyperbolic model, and it was developed by Duncan and Chang back in the 1970s. It's very popular in the 1980s, very, very popular, and it replicates non-linear hysteretic behavior of the soil quite well. That is a kind of small strain behavior, and Duncan and Chang actually try to use it for soft soil. The main weakness is that it cannot reproduce the shear volumetric coupling. That is, when you shear the soil, you get dilation or compression. That you cannot do. So as a result, it was very quickly realized that this model has a problem. When you want to use effective stress and you want excess pore water pressure, this model cannot give you the correct excess pore water pressure. Okay, so basically, if you used it before the yielding occurs, like for example, before the peak strength, I have used it before peak strength, it works okay because there's not much significant pore pressure generation, and so you can still get away with doing this. Actually, I dispute that the hyperbolic motor is totally useless. I actually find it quite useful in certain, but you have to apply it intelligently. Yeah, okay. So basically, you can use it in a total stress context for undrained problem. I mean, I work with Subhadip Banerjee on earthquake, and we use it as a total stress problem because it's an undrained problem, so there's no volumetric change, and we decided that we need to forego about the excess pore pressure and just try to model the stress strain behavior of the soil, right? So we were able to get some reasonable result. Okay, so that is okay if you know what you want and what you don't need. Okay, for drain problem, well, you may find that your volumetric compression and dilation can affect your overall ground movement, and then you may need to want to be a bit more careful with using it. Okay, I would hesitate to say no, you cannot use it, but you have to be a bit more careful. All right. So this is the Duncan Chang hyperbolic model. The second one is the Plexis hardening soil model. The Plexis hardening soil model, I think many of you are already. How many of you have used the Plexis? You have used Plexis hardening soil model. Basically, to me, one of the biggest advantage of the Plexis hardening soil model is this E50, EOED, EUR, because they allow you to reflect the non-linear stress strain behavior of the soil inners. Okay, but none of this is actually, it will overcome this some of the elasticity problem of the camp clay. Some of the elasticity problem of the camp clay. But you need to get the parameters properly. I think that's the most important thing. Okay. Okay, we recently produced a model that I think, I'm not saying that you should use this. I'm not even sure whether it is working in all situations, but we actually published this in the ASCE International Journal of Geomechanics, and what we did was that we actually did a trick on Berland's. You can see this. We actually did something to Berland's dissipation function. You see, this is the equation. Berland's dissipation function is just simply MP prime, and then this part is the same. We just added a C to it. Okay, and we said that the shear strain is not just doing work on the frictional component, is also doing work on the cementation component. And we allowed the cementation component to decrease, okay, with shear strain. And so basically, you come up to a new kind of U locus that is non-elliptical, okay. But when you you can compare with some of the test data. Experimental data is in broken line. Our comparison with various parameters are in the full line. So you can see, by and large, the kind of trend is okay. There are still some discrepancy in detail. Okay, so these are examples of models for structured soil. And the thing is that what you find is that actually none of the existing models, the soft soil model, the hardening soil model, chem clay model, modified chem clay, original chem clay, more Coulomb, whatever, in all these standard programs, none of them will model this kind of structured thing. Okay, and the thing about structured soil, if you ever hit a structured soil, one of the things that you will be you can use to see whether the soil is structured or not. If you look at this, in terms of the stress strain curve, they are all having a peak strength and then come down. You see that? Peak strength and come down. But when you look at the stress path, the stress path is very telling, because in a heavily over consolidated soil, you will also have a peak coming down, right? You also have a peak and then coming down, but your stress path is going to the right. In this case, the stress path is going to the left. But the stress path is not just going to the left and just stopping here. It actually comes down like this. This is quite common, quite typical of structured material. In the sense that when you reach the peak, the soil starts to shear. And when it shears, the structure, the cementation is lost even more quickly. And so as a result, the guy just comes straight down the critical state line. Alright? So it has the angle is the same, but you lose a lot of effective stress. Because the soil is collapsing volumetrically, and so you generate excess pore water, a lot of excess pore water pressure, and so your effective stress is dropping. For the same angle of friction, the deviator stress is dropping. Okay? So this is roughly how a structure, you can actually tell a structured soil from a heavily over consolidated soil. Heavily over consolidated soil will show you a stress path that goes that way, okay? Or go up and then come down this way in a drain situation. In the undrained situation for structured soil, you see something like that, that is quite likely to be structured soil. Okay? So the stress strain curve itself may not be telling. The stress path may be more telling. Okay? Right. Now, all said and done, there is actually no perfect model. There's no such thing as a perfect model. If you are doing work, the title of this course is for engineering practice. I think for practical something, I can't remember what is it. Constitutive modeling for practical geotechnical analysis. And in Singapore, I think that in future, I don't know whether in practice in India now, is it common to use finite element software? Common, right? In Singapore, you almost cannot get a job done without FEM. They will not allow you to start work. Planning authority, building and construction authorities will not allow you to start work unless you do FEM. Okay? And I had this course with them in mind, those practical engineers. No, they don't have time to go and develop model. They don't have time to write their own code. They are using standard code. So you are stuck with standard model. So basically, in a situation like that, there is obviously no perfect model that can model every soil under every stress situation. And natural soil is even more complex. Okay, so every model is really an approximate to real soil behavior. Now, you may say, hey, is this peculiar to soil? I tell you it's not. It's not peculiar to soil. I can tell you, if you look at the stress strain curve of copper wire, you know the copper wire stress strain curve I show you many times. Basically, the stress strain curve of copper wire is like that. Alright, and then you go like that. Now, how would people model something like that for copper wire? I tell you, they would use something like a Tresca or one Mises, which is like that. That kind of stress strain curve. And they will the metalworking people will happily do it. Now, for mild steel, it's the same thing. The mild steel, the stress strain curve is very complicated. Come up, down, and then go up this way, and then slowly go up there. Alright? But people will just use elastic, perfectly plastic model. They're quite happy to do that. So, it is not as if the soil people are the first one to do this kind of thing. Okay? Because ultimately, at the core of it, at the heart of it all, Material modeling is essentially an empirical science. If you ask how to prove how to prove Hooke's law from first principle, it's very hard to prove. Because all that Hooke says is that I found that force is proportional to displacement. But how do you prove force is proportional to displacement? It's not easy to prove. So basically at the heart of it, or a lot of it, is actually by observation and empiricism. And I can tell you that when people tell me about complicated constitutive model, usually what it means to me is this. You're fitting a very high level curve to what is essentially a set of material behavior. It's nothing but curve fitting. It's nothing but curve fitting. You're fitting a curve to material behavior, and basically you're saying that this curve, I think, describes this material. But there's no reason why this curve should describe some other material. You know what I mean? For so many soil in the world, it's very hard to say which model is suitable for which soil. Okay? And I think in a sense, that is why Andrew Schofield told me that don't do research in constitutive modeling, because you will never come up with... Basically what he says is that Cam Clay already made him famous. You are not going to be more famous than Andrew Schofield doing constitutive modeling, because the first guy already taken the grand prize. Right? You are the number 50,001. What prize are you going to end up with? That's what he was trying to say. So basically, I kind of pity people like Andrew Whittle. They spend half their life. Andrew Whittle has got at least 4 models. MIT model. Andrew Whittle is professor of Geotechnical Engineering in MIT, but he's the only guy, so we can bully MIT because we have got like 10 different people. He got 1. So, but anyway, I'm not saying anything bad about Andrew. But he spent half his life developing MIT E1, MIT E2, MIT E3, and then later on he got MIT S1, and I don't know whether now he got MIT S2. You ask me, how many people in India use this? Probably like that. Correct or not? Probably only Andrew Whittle himself. How can you be famous? You know what I mean? You cannot achieve international fame. Okay, so basically that's the key to the whole thing. So constitutive modelers, yes, but you should do it as part of something if you really find a need to do it, not because you want to do it. Okay? The great days of constitutive model. I always feel the same about Imperial College. I'm not trying to run Imperial College. I'm a Cambridge guy, and we have this running battle with Imperial College. And I think that a lot of those Imperial College guys are a bunch of pricks, honestly. I dealt with them before, and I think they are really a bunch of... I don't know. City University used to have their running quarrel with Imperial College. Matthew Coop and various people, John Atkinson. They used to have the running quarrel with him. But Imperial College people are very... They like to tell you that I'm the best and you are nothing. And not many people can swallow that kind of thing. So basically, that's. I think that there are a bunch of... I don't know, there are a bunch of characters. They don't even talk to each other. So anyway, the problem with Imperial College is that their repertoire is very restricted. They only do triaxial testing, constitutive modeling with a bit of finite element. Zrakovic is carrying on David Potts' work, but really, how far can you push all this kind of thing? All right. The nice thing about a lot of these people like Mark Randolph, they got physical modeling. So he basically added one dimension to it. You got physical modeling, you got FEM, you got constitutive model, you got triaxial tests, you got all kinds of things, you got field tests. So basically, you really want to have as many repertoire as possible in current soil mechanics research. So don't restrict yourself to a triaxial test. I do triaxial tests, but I think that you need to don't rule out field data. I think field data can be very rich. Okay, so advanced model may give a better approximation, but they are also more likely to have more singularities and quirks which even their developers are not aware of. And the most important ingredient in the FE analysis, I strongly believe, is not the software or the constitutive model, but the user doing it. You are the most important element. All right? It will be a very sad story, sad day, if the day comes, somebody tell you there is this constitutive model so good, It will prescribe the parameter itself. You just press a button, it will run. Because what it means is that you just need a primary school graduate who know how to press the computer button and the guy give out the solution. What is the relevance of the geotechnical engineer? Zero. You know, geotechnical engineering will be dead. All right. They always say that there are times will come when the PC will diagnose your illness and your doctor is not needed, your GP. Until today, people are still going to the family doctor. There's no such thing. The element of judgment, the human touch is still there. You know, FEM involves many other approximations apart from constitutive modeling. Constitutive modeling is just part of the equation. FEM involves a lot of other things. So you got to think through. By right, if you really want to do a good job FE analyzing, you really have to do a fair bit of thinking through the whole problem before doing it. And basically, constitutive modeling is just part of the thing that affects the answer. Loading and construction sequence, geometry, all these affect the answer. And they have equally important effects. And there's usually insufficient soil data to use the latest model. So you must maintain a sense of balance and proportion. A sense of balance and proportion. Of course, in your report, I like to see consulting report which basically gives some justification of why you are using this model. And that's important. Why you are using this. But it doesn't mean you have to use the best. There's no such thing as the best. Okay? So essentially, you don't want to end up being caught in a constitutive modeling frenzy. Okay? Now, better than to use the most advanced model available, it's better to have a more important to have an understanding of real soil behavior coupled with an understanding of which aspect of soil behavior is likely to play an important role in your problem. This will allow you to choose models and parameters which adequately reflect the most important aspects of the behavior. And I'm going to show you a few problems. I'm going to start off a few things, and then afternoon I will continue and also continue tomorrow. Afternoon I'll do 1 hour, right? Then after that I will leave the rest to tomorrow. I think I shouldn't have a problem finishing. I think I should be okay. In fact, tomorrow I think I will probably finish around 10 o'clock. Okay, and you can use the other half an hour. But today is a deadline, so tomorrow you can take it for tea break or something like that. Okay, so for example, in the nickel highway collapse, the problem was one of collapse, and the strength is something you need to model properly. Because I always say this. Let's take a very simple situation. The soil in a nickel highway, say you plot the stress strain curve, the soil has gone through this thing, and now it's somewhere out here, and it's literally gone critical state. Right? You think the guy can still remember what happened down here? Probably cannot. All that you need to do is to make sure that this level is properly captured. Right? Because this is the strength itself that will allow the thing to fail. So basically, you make sure you capture this thing properly. So in that particular problem, we know the factor of safety was less than 1. Because the thing actually collapsed. Right? So we know that this is the most important thing. On the other hand, if you have something where the factor of safety is reasonably good, you look at it, it is a stiffness control problem. I don't care whether you use a hyperbolic or you use a representative E50, make sure you capture your stiffness reasonably well. And your answer is good. And I can show you an example. The Fort Canning Tunnel is a classic example. I used the simplest more Coulomb. I used method A. I even went up there to justify to the government people. I said, why I use method? I said, look, this is okay. This material is fine. It's not soft soil. This material is fine. You look at the A parameter is 0, no? The A parameter is 0. I said, why can't I use more Coulomb? And I used more Coulomb, and I did a series of parametric study, come up with a representative E50, and the answer is almost spot on. And I don't know the answer when I was modeling it because it was before construction. About a year and a half after I modeled it, we saw the answer, and I was surprised by how good the thing was. Okay. So basically, the way I see it is, you don't have to use the best model. You can, but the guy who uses it needs to have a lot of skill. Okay. Okay, so this is the Fort Canning Tunnel, and so basically it's a more Coulomb with effective stress parameter is fine. Okay. Now, oh, this is not the end yet. I suddenly realized there's a big chunk of thing down here. Okay, I missed out, sorry. Okay, now, it is also important, you have to tell, now I want to say something about this because, this is an important part. Because many of you will be using Plexis. I think some of you are already using Plexis. Okay, now there is a big confusion. There was a big confusion in just following the nickel highway collapse. Because everybody thought the Plexis soft soil model is modified chem clay. Now, the thing that added to confusion was this. The Plexis soft soil model also used an elliptical U surface. So they use an elliptical U surface on the wet side. On the dry side, they use the Mohr Coulomb. So basically, they have, on the dry side is a straight line, on the wet side is an elliptical curve. Okay, so basically, there was a lot of confusion, and so there was a lot of discussion, and in fact, one of the first set of comparative results came out from Wong Kai Sin in 2005 in the Underground Singapore 2005, in which he compared the soft soil model with the modified chem clay. The soft soil model and the modified chem clay. And his result shows very clearly that the soft soil model, for the same friction angle and everything else, compression index, swelling index, everything else, the soft soil model will always give you an answer that is about 15 to 20% higher than that of the modified chem clay. Now, Kai Sin was not able to explain why that is the case. So we subsequently did a bit of study on ourselves, and the answer became quite evident. When you look at the way, so that's why I say you got to understand how the model works. Alright? I have given you an understanding of how the chem clay works, right? So now we've got to look at how the soft soil model works. And I think this will be of importance to you when you use the soft soil to know how it works. Now the soft soil model in Plexis, I just want to recap. The soft soil model in Plexis consists of two envelopes. The first on the left side is what you call the Mohr Coulomb. That's a standard Mohr Coulomb. The standard Mohr Coulomb envelope. That on the dry side, on the wet side, this is on the dry side. On the wet side, on the left side. Then on the right side, they couple it with the elliptical U surface. Elliptical U surface. Alright? Elliptical U surface. Now, the difference, this is where the catch is. The Mohr Coulomb part is not the issue because most soft soil will be on the right, far to the right. So you'll be following the elliptical U surface. And so a lot of people came to the conclusion that it will behave just like a chem clay, right? But it doesn't behave like a chem clay. Okay, let me just revise how the chem clay model is put together. The blue ellipse basically show the chem clay, and this angle of friction, which is deemed to be the critical state angle of friction, passes through the crown of the ellipse. Is that alright? That is for chem clay. Passes through the crown of the ellipse. On the other hand, for Plexis, this red ellipse doesn't pass through. The crown of the red ellipse is here, but the angle of friction is here. The angle of friction is here, but the crown is here. So the failure envelope, or if you like, the critical state line, doesn't pass through the crown of the ellipse. So, in fact, the soft soil model is not a critical state model. It doesn't model you up to the critical state. Now the question is, how does Plexis prescribe this U surface? It turns out that Plexis prescribed this U surface in a rather roundabout way. You specify the angle of friction, right? You specify the angle of friction. Modified chem clay is very straightforward. I fitted an ellipse so that the crown of the ellipse passes through that M value, correct? Now, Plexis doesn't calculate the M value directly. It doesn't calculate. What Plexis does is, you give it 25 degrees, the guy will go to Jakey's relationship and say K0 equals 1 minus sine phi. Alright? That gives you the K0 value. Okay? And then what Plexis does is to fit an ellipse through so that when you put it through one-dimensional consolidation, it gives you that K0 value. So what Plexis is doing is to take the angle of friction, use Jakey's relationship to deduce the K0 value, and fit an elliptical envelope based on that K0 value. So Plexis is matching is matching K0 value to what is Jakey's prediction. Is that all right? Based on the angle of friction. Based on the angle of friction. And that is the reason why you find that the ellipse because you remember I told you that the modified chem clay typically predicts a K0 that is higher than Jakey's. Right? So Plexis try to correct for that by pushing up the ellipse so that it gives you back the Jakey's K0 value. Now, I'm not sure. It is arguable as to how important this is. Obviously, the Plexis people think this is important to get the K0 value right for the soil. The K0. I'm not saying that it's not correct. This is correct. But my question is, how well do you really know the K0 value of a soil? You know, if you read Schmidtman in America, Schmidtman will tell you K0 is one of the most unknown parameters in the real soil. Because on a level ground, everything uniform, horizontally layered, your K0 is still fine. If you have a sloping ground, how do you K0 the thing? I mean, basically that is, but this is the Plexis philosophy. This is the starting point. But whatever it is, it leads to an ellipse that is higher. And this is an illustration of the thing. It leads to this red ellipse as opposed to, so a 25 degree, if you specify an angle of friction of 25 degree for chem clay, you will give you the blue ellipse, the broken ellipse. It will give you the Plexis red ellipse. Not the same. They are not the same. Now, remember what I mentioned about the undrained stress path? The undrained stress path is always just above guided by the U locus, right? So if you have something that looks like the chem clay, the undrained stress path will be the flu line down here. This is the undrained stress path. The Plexis undrained stress path will hit somewhere here. So it will hit the failure envelope here, and this is the failure strength. The failure strength is about 140 over, whereas the chem clay will give you a failure strength of 118 or 119. So that accounts for the 10-20% difference. Okay? So basically, the idea is that Plexis will, because after the nickel highway, there was a big concern about we better make sure we capture our strength properly. And it turns out that if you use the Plexis, some people will say, oh, if you use the Plexis soft soil, everything is soft. But then Wong Kai-sin shows that if you use the Plexis soft soil, everything is not soft because you're still 20% higher. You're still 20% higher than the actual undrained shear strength. So it turns out that for Singapore marine clay, the critical state model, which is the chem clay model, works reasonably well for, this is the irony. I'm not saying that it works for everything, but for Singapore marine clay, it seems to work very well. And whereas the Plexis will always give you slightly higher. Now, you can actually tune your Plexis model to give you the same strength as a chem clay. For example, in this case, if I use an angle of friction of 17 degree, m equals to 0.676, then the Plexis stress path will come up to here and it will be stopped by this failure envelope. Alright, it will be stopped by that failure envelope, and then you are getting almost the same kind of strength level. And so basically it is exactly the way you do for Mohr Coulomb angle of method of compensating error. You just lower the friction angle to stop the guy earlier. You get what I mean? So basically this is the difference. So when you use Plexis, be careful, read through the material model first. The trouble is that, you know, when I ask my students and my clients outside, they are engineers, they are using Plexis, and I said, have you ever read through the Plexis theory manual? No. I only found out which button to press. But that is actually not the most important thing. How the guy handle it, how the guy handle what you press is more important than what you need to press. You know. So this is basically one of the things about Plexis. Now, the second thing is this. So basically, the Plexis for the same angle of friction will give you something higher. Okay, and so in order to lower it down, you have to use possibly a lower angle of friction. Instead of 25 degree, you may use 17 or 18 degree to kind of compensate for that, to be in line with the chem clay model. All right. Okay, now it's for Singapore marine clay, we have done quite a bit of tests, and we show that actually in most cases, the modified chem clay, ironically, the modified chem clay is not considered the most accurate model for soft clay, even for kaolin. But ironically, strangely enough, for marine clay, it seems to work quite well. For our marine clay, it seems to work quite well. Right, now, what I showed you there was remolded marine clay behavior. Remolded marine clay behavior. Now I'm going to spring a shock at you. And the shock is natural marine clay. The important thing is this. Those of you who are working, how many of you are working outside, have worked outside or are working outside or have done consulting jobs or whatever, done engineering practice? How many of you? You have dealt with soil investigation. You have dealt with sampling, right? Have they ever tell you that most samples are killed before they come to the lab? You completely failed. Okay, you know what is the logic of that? And this is not a joke, it's a truth. So for your next time when you work outside, you may, under the right circumstances, want to pay attention to some of these aspects. And David Hyde, who was, I don't know which year he was ranking lecture, 2000 and something, I can't remember. He never wrote his ranking lecture up. He refused to write it up. He has a big quarrel with Brian Simpson, refused to write it up. But David Hyde is a good man. Although he's from Imperial College, he's the one exception. I call him the perfect British gentleman. You know, a real British, when you meet you, there's no such thing, I'm a ranking lecturer, who are you? There's no such thing. He tells everybody the same thing. He doesn't talk about himself. He's a real, have you met him? David Hyde is a real, he and David Potts are two different kettle of fish. David Potts, I don't know you, why you talk to me? The guy can actually tell you that, offhand, just like that. David Hyde is he's a real British gentleman, he's actually nicer than Andrew Schofield, okay? And David Hyde is very concerned about sampling effect, okay? Now, it turns out that sampling effect can be looked at in a very simple way. When you go to a site, especially soft soil, you jack your sampler in, right? And your sampler is a tube, is a cylindrical tube with a sharp edge, okay? So a cylindrical tube with a sharp edge that goes down like that. And then, just exaggerating the dimension, sharp edge. And you push into the ground. And so maybe the ground surface is somewhere up here, okay? Doesn't matter. You're pushing it in. And there is some soil already inside here, okay? Some soil already inside here. And you're just jacking the tube in. Just jacking the tube in like that, okay? Now, there's a lot of things sticking to the side of the tube. Firstly, the soil here is sticking to the side of the tube, right? It is sticking, so there will be a drag. So when you push your tube down, you're trying to push this plug of soil down at the same time. On top of that, your soil outside is also sticking to the side of the tube. That's the reason why you need so much force to check it now. So basically, if you look at the element of soil just in front of the cutting edge, when you press your tube down, you're almost doing a triaxial compression on the soil. Alright? And then when you push it in, when this guy got into the tube, it probably started to relax a bit. So basically, Clayton and, I can't remember the paper by Clayton and somebody in Geotechnical, when they look at this problem, what they say is that you actually put the soil through one cycle of triaxial compression before it even got into the sampling tube. That's why I always have this joke to tell, I say, an undisturbed sample is a very heavily disturbed sample. A disturbed sample is a completely destroyed sample. In soil, that's the way it works, alright? That's the way. So most sampling tube, including the Shelby tube, the classic standard is called the Shelby tube, have this major problem, okay? And of course, you can obviously, there are ways you can actually mitigate this effect. One of the ways is this, they use what they call an inner clearance. The inner clearance is a thing that says, around the tip here, I curve my tip in a little bit, so that the opening here is slightly smaller than the diameter inside. So you got inner clearance. So basically, this is to lessen the tendency of the sample jamming inside here, sticking inside here. So basically, once the sample gets past this tip here, it is able to detach itself from the wall and thereby slide in easily. The danger about that The weakness, the drawback with that is this, that you end up with a sample with a small gap between the sample and the wall of the sampling tube. So over a period of time, the sample will lose effective stress. It will start to swell. It will lose effective stress. So you got to be careful with that. All right. Or if you have the wall tightly around the sample, then the tendency to swell is not so much. But if you allow the sample to just clear the wall, then it will start to swell. So as a result, over a period of time, when you take it out and test, maybe 3 months later, if you wait for 1 month or so, take out and test, you may lose some effective stress. So you got to be careful with that. All right, that's one. Now, there are other ways to do it, and one of the ways to do it is, of course, make this wall as thin as possible. Actually, the thing that is important is not the thickness of the wall, but the thickness of the wall relative to the diameter of this thing. Okay? And I don't know what's the size of the sampling tube you use here, but typically in Singapore, we are using 3-inch or 75 millimeters. Are you using 75? 70, 75, that's the kind of thing, sampling tube. Now, so basically, with this kind of thing, the Japanese have a similar size, but they have very thin wall for soft soil, and they use piston on the end. But on top of that, and this is where the Japanese are smart. The Shelby tube prescribed an angle of 20 degrees. The Japanese sampler tip is 6 degrees. It's a 6 degree tip. So basically, it's a lot sharper, a lot thinner, and it is supposed to sample the soil. So when we work with the Japanese, these samples are all taken using Japanese thin wall sampler, not the Shelby sampler. Okay, so with the Shelby sampler, it's all cute, completely cute. You can't see anything. There's no more structure left in the soil whatsoever. It's like remoted kind of thing, you know. So basically, this is the thing with sampling. And so basically, but I think that you need to be careful. You need to be aware of the fact that sampling does disturb the soil. And one of the things I always recommend to people, but a lot of people may find it difficult to implement if your borehole is not big enough. My point is, instead of using a 3-inch sampler, why don't you use a 4-inch sampler? Because you know why? When we use a 4-inch tube with the same kind of wall thickness and same kind of angle, you find that actually the disturbance is much less. Because it's just, and you use the center portion, of course. You don't use the side. You use the center portion. Your wall displacement is actually, your sample disturbance is much less than a 3-inch tube. But it may require the on-site people to make some adjustment to their rig and the thing. So I do not know how difficult it is how easy it is to do this kind of thing. But this is one of the ways. Now, if you do something like that, and you look at Singapore marine clay behavior, I'm going to stop here and I will explain the rest later on because lunch is coming up. The shocking part is that structured clay behavior. Do you see this is the typical soft clay, remolded clay behavior? The Singapore marine clay behavior actually goes up like a black line all the way up. Did I tell you about the cemented soil behavior? Doesn't it look like a cemented soil? This is undrained stress path going all the way up and then coming down along the critical state line, generating structural collapse. You got structural collapse when you shear marine clay, and it's a very soft clay, and yet it is cemented. It is cemented. You see, the thing that is important, and this is the part that is not captured in the committee of inquiry hearing, because in a committee of inquiry there are 14 parties. One party representing the Singapore government, one party representing the Land Transport Authority, one party representing the main contractor, the subcontractor, and there are like 4 or 5 different subcontractors, and there are 4 people queue in there, and so each one represented by their own lawyers and their own, and everyone is trying to pass the blame to the next guy. I mean, this is what happened in a hearing, right? I mean, so the lawyer will take precedence. The lawyer will say something you better don't say, something you can say, something you better don't say. And consultant also have their own lawyer. You know the consultant was AECOM, Monsos. I don't know what's that called, Monsos now, it's called AECOM. AECOM. Yeah, AECOM, yeah. I tell you, John Endicott was the chairman of AECOM for Asia Pacific region. He had a hard time. He was a factual witness and an expert witness. Expert witness means you profess your opinion of the case, which is okay, you're not involved, but this is what I think, who is at fault. You know what I mean? That is okay. Factual witness means potentially you're liable. I tell you, John Endicott is a classic experience, and this is something I always learn. I say if there's nothing I learned by reading the transcript of the COI, this is one thing I learned. You know, he was up on the stand, and Philip Jeyaretnam, one of our top lawyers, Philip Jeyaretnam was questioning him, and Philip Jeyaretnam was asking him, he said, look, Dr. Endicott, and Dr. Endicott was my senior who worked under Andrew Schofield. I never had a good, I don't like him because I think the guy is he's a real old fox. He's a real old fox. So basically, he was up on the stand, and Philip Jeyaretnam was trying to pin the blame on him and say that, look, you are the chairman of AECOM. When all these things were happening, you were giving advice. You were obviously giving advice. Do you know what advice you give? Do you have a record of what advice you give? Where are your emails and all this sort of thing, And John Endicott was, of course, trying to say that, look, my main office is in Hong Kong. I don't come to Singapore very often. And Philip Jeyaretnam says, can you show me what emails transpire between you and the Singapore office? And John Endicott, without even hesitating, my computer has been attacked by a virus and the whole hard disk was reformatted. I tell you, this is something I learned. If somebody ever put me on the spot, I'll press that button, Control, Alternate, Delete. You must learn that. Because that can get you out of a lot of trouble. That was John Endicott. I tell you, it's just amazing. So basically, a lot of these things never came out of the Nickel Highway. I can tell you a lot of stories about the Nickel Highway collapse. Up to 2 months before collapse, one of our esteemed colleagues, I think you probably know him, go around telling people that method A is the one to use. And then after 2 months before the collapse, then suddenly one fine day he changed his mind and said, hey, you better don't use method A. Friend, I've been using it for the last 3 years, designed a whole wall based on method A. Now how you tell me not to use method A? The wall is already 30 meters down excavation, and you tell me, hey, sorry, you can't use method A. What do you want me to do with the wall? So basically this is the situation. But anyway, the important thing is this. You can see the marine clay is actually going this way. And nobody, take a look, everybody was looking at it as if it's a remolded soil. But in fact, marine clay doesn't behave like that. And I always ask the question, I said, if the method A is that obvious, I'm not saying it's wrong. As a design approach, it's correct. If the method A is that serious, why is it there was no collapse? Method A has been used since like the late 1990s, 2000, and then all the way to 2004. There was no collapse. In fact, Nishimatsu, who was the main contractor, said, oh, no, we do this all the time, no problem. Why there was no collapse? Obviously, there were other triggering factors. You see, the thing is this. I always tell people, if you see a material like this with the stress path that go like that, okay, if you use method A, it will give you a vertical stress path, right? And that is fine, as long as you don't exceed somewhere around here. As long as you don't exceed there, you have enough factor of safety, your method A is okay. The only problem is that if you happen to go up to here, and then you try to go up further anymore, it will come down here, and then you get a double whammy. Then you get a real problem on your hand, because you can't stop the guy. The soil is structurally collapsing. You can't stop the guy. You know what I mean? That is the problem. That to me is the real problem with working with a structured material like that. But it doesn't mean that you shouldn't use method B. You can still use method B. In fact, I would use method B. I would say I cut the thing here. Or I use a small angle of friction to cut it there. That's why it's still doing that. But it is not because the stress path is totally wrong. The stress path may be actually reasonably correct. The vertical stress path for a structured soil. For a less structured soil, you probably get the thing turning back. The classical leftward turning stress path this way. But this is a structured soil. Sensitivity of about 3. You can see that there is actually an effect of the structure coming out. Okay. So the question obviously the next thing is, well, how should I prepare? How should I model something like that? And so I will try to give you a few suggestions on how to model it. Maybe after lunch. Maybe after lunch. Now it's already 12:40. We gather here at about 10 past 1. 10 past 2. 10 past 2. Yeah, 2 to 10 past 2. Then we continue the thing, and then we'll see how far we can push. Okay? I'll try to say a little bit out. What I'm trying to do is that after this, I want to talk a little bit about finite element modeling and how you should take care of the other things. Wow, quite a lot. Finite element modeling and things like that. So I hope to say something about that in after lunch. Is that okay? So I think I'm doing fine. Let me see where I am. Okay, I'm about halfway through the thing. By the afternoon, I should be up to about slide number 60 or past 60. I think tomorrow morning we should be able to finish it in good time. Okay, maybe about 1 hour I can clear about 10 more slides. After that, I should be able to do a bit of let you off and do the hands-on. And then tomorrow we have 1.5 hour. 1.5 hour. That should clear. Okay, we are doing fine. Okay. Any question before we go? I would say it is more elegant. I don't know why you say it's safer. Safer than what? Safer than just undrained shear strength. Oh yeah, definitely it's safer than actual friction. You can't. I mean, you use the friction. You see the problem with using the actual friction angle. All right. If you use chem clay, it will tell you that you end up here. That's what I'm going to tell you afterwards. It's going to tell you end up here. If you use, because you see the soil is actually over consolidated. The OCR, the over consolidation ratio, is about 1.5 to 1.6. So that's the reason why if you respect that over consolidation ratio, you will end up down here, where the failure strength is down here. Where you end up here, you should end up here. But you will end up here, which is wrong. In fact, you're too high. If you use more Coulomb, you go even higher over there. That is even worse. All right? Now, the question is, are you able to capture this good stress path with this thing? Very difficult. Because the thing coming down is not something that most model can deal with. You know? Okay? That's why a lot of people tell me, oh, Plexis hardening soil can do everything. Can you do this? Cannot. No model in any commercial program, even Abacus cannot do this. Okay? Flag, Abacus, GeoFEA, Plexis, none of them can do this. Okay? Can? Okay? Can? All right. So we'll meet again after lunch. Okay? And then we'll continue from there.